Hello, everybody. This is Professor Ma, and this is the sections more on logging exponential equations. Uh, there are basically two types of exponential log equations. One type that we need to use a calculator, and one we don't. The ones that we don't, usually that is related to conceptuals, how do you manipulate the equations using rules to simplify them into linear or second degree equations? Okay, and usually we use the following two rules. That is so-called uniqueness of the logarithm functions or the exponential functions. Uh, in log versions, is if log of two numbers, if u and v, and if I log using base b and wind up with the same answer, then the two number u and v must be the same number. Okay. In other words, the log functions are one to one. Two different inputs will yield two different outputs. So if the outputs are the same, the input must be the same. And the same thing we can say about exponential function. If you have b raised to two powers turns out to be the same number, then the powers that raised must be the same power. So we can what we're saying is if we have these, then we can drop the base, and then we can conclude the exponents must be the same. So let's take a look at how we use that to solve a log equation, I mean exponential equation. What type of, how can we tell the equation that we don't need calculators? One giveaway is that if a problem is phrased in terms of a common base number in the same family, like for instance, these numbers are all of base 2. So then the natural way to do a problems in base 2 is convert everything inside in base 2, and then we simplify the expression and see where we went up. Okay, so 4 is 2 squared, 8 is 2 to the third, so I write 2 squared and 2 to the third for 4 and 8, and it will look like that. And here actually there from here on actually it's a problems about collecting base. Basically we saying what is the exponents 2 squared raised to 2x minus 1, and what is the exponent 2 to the third power and raised on top of it 1 minus 3x power. Well, power to a power I can multiply them, so therefore those can be collected into powers for 2 to the 4x minus 2, then the 2 to the 3 minus 9x. But 2 in the front is 2 to the first power. So 2 times these, I add a power, so this will be 4x minus 2 plus 1. So I can simplify the exponents a little bit more. And now I have the exponents, the exponential from 2 raised to two different exponents turns out to be the same. So the exponents have to be the same. So I can extract exponents, and in this case it's a linear equation of that, and then I solve the linear equation accordingly. Okay. And if I put some, I'll put another extra x somewhere in there, so it turns x squared in the equation, then the extraction will be a second degree equation. So this is type of problems we don't need calculator. That is, we reduce it to a first or second degree equations. And here's a equation in log, similar type of situations. In the log, we have two different situations. One is after we collect everything. Notice in here, in the exponential situation is we'll collect everything into two exponents. The same thing we want to do with log. We want to collect everything into as much as possible. Now, there are two possibilities in terms of the log equations. So we start from here. Log plus another log is the turns into the product x minus 1 times x plus 3. Okay. The addition of log came from log of the product, and that is 5. Okay. Now, once we consolidate the log into one log, and now I can rephrase, drop the log using the base 2. I will have a second degree equations. Okay, 2 to the 5th, 32, then expand x minus 1 times x plus 3, and it's a second degree equations. And then I solve the second degree equation accordingly, and I get 2 answers. And make sure you check the answer makes sense. That is, when you put it back in there, we are not taking any negative numbers, log of any negative numbers. And 5 is okay. But minus 7 is no, because if I put minus 7, for instance, in x minus 1, then we'll be taking log of minus 7 minus 1 will be minus 8, and that doesn't make sense. So we can't have that. So therefore, minus 7 doesn't work. Another type is when we collect all the, simplify all the logs together, then we wind up with a situation where we have a log of somebody is equal to log of somebody, like the ones we begin in the very beginning, so the dropping the log, that log is a one-to-one formula. So we consolidate these into, right now there are 3 logs, and this rule does not mean you can just drop the log over here. It does not mean you can say, oh, I got 3 logs added, subtracted, then therefore the x plus 2, let me just drop the log, minus x minus 1, got to be 5. No, no, no. The rules only works as you have a single log equal to a log of somebody. One log into another equal to another log. Then you can conclude that U and V. Not having 3 of these. Okay. So what does that mean? It means I have to consolidate the logs into, on the left hand side, into 2 of them, into 1. Since it's a subtraction, so that's a quotient. Now I have a log of 4 is equal to log of 4 of some 5. So therefore the fraction has to be 5. Now, again, we drop the problem, transform the problem into in this case, a linear problem again. We multiply the denominator and solve. And this one actually works. Okay. Concerning other base, so how do we solve equations of other base? And here is an easy formula for change of base. So for any base b, I can write b these equations. Then I apply natural logs, for instance, to both sides, and then the exponents can come forward to the front, these exponents on top, come to the front, multiply into log of b. And what does this say? Well, this tells us what log of b of a number x is in terms of natural log. It's natural log of x divided by natural log of b. These we call the change of base formula. So one way to use this formula is I can solve a problem using log base b, and then when I need to get a numerical answers, I do this change of base into natural log, so I can use a calculator, okay, because log b is not on the calculator. Okay. So here is an example. Okay. So I want to solve for x, so I divide by 3, and here is the exponential problem in base 5. So one way to solve these problems is solving in base 5. So 2x plus 1 has to be log base 5 of 14 over 3. This is one way to do this problem. Okay. And then I can solve the x as minus 1 on both sides and divided by 2. Okay, so this is the answer in base 5. But I have to change your base formula. Log of base 5 of this is natural log of this of 14 divided by 3 divided by the natural log of 5. That was what the change base change formula says. Okay, then now I substitute by natural log. And this I can use a calculator. Okay, and this is what the numerical answer is supposed to obtain. Okay, and here is another example. One way, okay, there are a couple of ways to do this. One way to do this is just apply natural log directly. But this, on the PowerPoint, I use base 4 to solve the problem. This is one way, another way to do it. And then apply log base 4. Then log base 4 of 4 to the x minus 1. Remember, this is exponential and log inverse, so I just get x minus 1 on the left-hand side. On the right-hand side, then the exponents multiple comes down, and I put that to the back. Okay. This I can solve for x. Expand these times that, and move the x together. Extract the x, factor it out. Then divide the coefficients, multiply these in the front, the multiple in the front, divide these underneath as a fractions. And then I get an answer in log base 4. Okay. Then you look at calculator, oh, wait a minute, I don't have log base 4. Well, you have LM base change formula. Log base 4, 7 is log 7, ln 7 divided by ln 4, okay, and then we can figure out what this is using the calculator. So this is one way to do it, okay. Or else you can apply ln directly and solve for the x. So yeah, do the homework, and that's it. Until next time, bye-bye.